So today I'm going to be talking about hypergraph rewriting systems, how we can define a kind of categorical semantics for hypergraph rewriting, some of the compositional, algebraic, and homotopic aspects of that of such rewriting systems, relationship to things like homotopic type theory and higher category theory, and also I might talk a little bit about some more speculative ideas about what hypergraph rewriting systems may be able to tell us in regards to kind of the foundations of physics, but we'll see whether or not I get there. But okay. Oh, and I should say, if people have questions, feel free to like interrupt me kind of partway through. I don't particularly, just shout out something. Okay, before I actually start though, I should just say that much of what I'm going to be presenting here today is work that was done in collaboration. So a lot of the kind of work on the compositional aspects of these rewriting systems, and particularly the relationship with quantum information theory and the ZX calculus, was work that was done in collaboration with Monognia Namaduri and Xerxes Asawala. The connection to higher category theory and these higher these kind of n-fold category constructions for rewriting systems, that's work that was largely pioneered by Xerxes and also done in collaboration with Hatem El-Shatlawi, and also the connection to sort of homotopy type theory and these homotopic aspects of rewriting systems is again work that was largely done by Xerxes, which I shall be shamelessly taking credit for today. But okay, so what exactly are we dealing with? So as most of you probably know, a hypergraph, you can just think of it as being a sort of generalization of an ordinary graph in which hyperedges can connect any arbitrary sort of non-empty subset of vertices. So you could have hyperedges that are either ordered, in which case they're sort of ordered lists of vertices, that's the analog of like a directed graph, or they could be orderless, in which case they're just sets, and that's kind of the analog of an undirected graph. And then with a hypergraph that's defined in this way, we can define rewriting rules on it. So we can define abstract rewriting rules that effectively just say, if you've got a sort of sub-hypergraph that matches some pattern, then replace it with a different sub-hypergraph that matches some different pattern. So for instance, here we've got an example of, these are ordered hypergraphs in this particular case. We've got on the left an arity 2 ordered hypergraph, which is just a directed graph, 1, 2, 1, 3, 2, 3, 4, 1. And on the right, we've got an arity 3 directed hypergraph, 1, 2, 3, 3, 4, 5. So in general, I'll represent these hypergraphs as just lists, as kind of nested lists of hyperedges. And at the bottom here, we've got an example of a hypergraph rewriting rule. So here's a rule that just says, if you've got a hypergraph that matches this pattern x, y, y, z, then you can replace it with one that matches the pattern w, y, y, z, z, w, x, w for some introduced variable w. And so you can represent it graphically like that. And so then if we take some initial state, some, like say a hypergraph with a double self-loop initial condition like this, and we just repeatedly apply that rule that I gave on the previous slide in accordance with some canonical updating order, and I'll talk a little bit more about that in a moment, then we eventually derive something like this. So after 14 evolution steps of 14 steps of applying the rule wherever it can be applied in some non-overlapping way, we eventually get something rather complicated looking like that. Okay, so the question is, can we describe a little bit more formally what's going on when we do hypergraph rewriting? So our initial setup is we use this definition of a hypergraph category that comes from Kissinger and Fong. It's a slightly technical definition involving these special commutative Frobenius algebras, but kind of more intuitively, one can think of a hypergraph category just as being some category whose associated string diagrams are hypergraphs, and hypergraphs in the ordered hypergraphs in the sense that we defined on one of the previous slides. So in effect, what we're doing when we do hypergraph rewriting in this way is we're just taking the ordinary techniques that one might use to do string diagram rewriting, and we're applying them, but to a category that happens to be a hypergraph category. And so in particular, the so-called double push-out rewriting formalism that's kind of traditional in sort of algebraic and compositional graph rewriting, we can translate that to, with fairly minimal modification to the context of these hypergraph categories. So in particular, we can define one of these rules as a typed hypergraph production. So in this case, it's just a span of monomorphisms, which I'll call P. So in this case, we have K, which is a typed hypergraph that represents kind of the invariant subhypergraph. So when we apply a rule, we sort of match the left-hand side, we replace it with the right-hand side, and then there's a surrounding sub-hypergraph that is kept invariant by the application of that rule. So we call that K, and we call the left-hand side of the rule L, the right-hand side of the rule R, and then we have one injective morphism from K to L, and we have another injective morphism from K to R, and that span is effectively our rule or our production. And then to actually apply that rule, what needs to happen is that rule has to match somewhere. So for us, a match just means a morphism from the left-hand side of the rule to the full hypergraph G. So if such a morphism exists, then we can apply a direct transformation from the hypergraph G to the hypergraph H. And in that case, this transformation is just given by effectively a push-out complement square, which you see on the left here, which sort of intuitively what that's doing is it's saying I take the full hypergraph G, I extract out a subhypergraph that's isomorphic to L, and I leave this invariant subhypergraph K. And then there's a corresponding push-out square on the right, which effectively says, then I take the right-hand side of the rule R and I glue that back in to the invariant subhypergraph, and I get this new hypergraph H as a consequence of applying that rule. So that's how we can encode one of these rule applications. Compositionally, that gives us a direct transformation. And then any transformation between typed hypergraphs that's permitted by these rules is just then a sequence of these direct typed hypergraph transformations. Okay, now that all sounds quite straightforward. It turns out it's a little bit more subtle than I've made it seem. So ordinarily, again, in the classical theory of compositional graph rewriting, these double push-out systems, these DPO systems, are defined over what are called adhesive categories. An adhesive category is one, loosely speaking, in which the monomorphisms are sufficiently well behaved that you can do this gluing operation of extracting the left-hand side and gluing in the right-hand side that I described before. So formally speaking, it's an adhesive category is one that has push-outs along monomorphisms, it has pullbacks, and every push-out along a monomorphism satisfies this rather technical condition called the Van Kampen square condition. So I won't talk too much about the technical details of that, but basically what I mean by a push-out along a monomorphism is if we have a span like A goes to B, A goes to C, in which either of the two morphisms is a monomorphism, then the corresponding push-out of that span is called a push-out along that monomorphism. And then we can say that such a push-out along a monomorphism satisfies this Van Kampen square condition if, when we look at this commutative cube here, and in particular, if we look at these subdiagrams, these two faces of that commutative cube, these faces correspond to pullbacks, and the pushouts and the pullbacks obey some sort of obvious compatibility conditions. So I'm not going to, again, we don't really have time for me to go into a huge amount of detail about precisely what the Van Kampen square condition means and why it's required. If you want to know more about that, either read our the second paper in our sequence of ZX calculus papers, which has a whole section about why it's required for the case of these hypergraph categories, or go and read, for instance, some of the work of Alex Kissinger. So for instance, Alex's PhD thesis has, in my view, one of the most coherent explanations of the Van Kampen square condition and what its significance is that I've seen anywhere else. Anyway, all of which is to say that our category of typed hypergraphs is not adhesive strictly by this definition. And the reason for that is effectively because our hypergraph vertices can be connected in some rather arbitrary way, these push-out along monomorphisms are not even guaranteed to exist, let alone to obey the Van Kampen square condition. So it's not possible naively to define double push-out rewriting over one of these typed hypergraph categories. But as it turns out, that isn't so much of a problem, because you can, what we were able to show in the first ZX calculus paper that we wrote was, again, quite a complicated technical proof that uses this construction of typed open graphs due to Dixon and Kissinger. But what we were able to do was to show that our category of typed hypergraphs is nevertheless partial adhesive, which means that there's an embedding functor from a full subcategory to some adhesive category, such that that embedding functor preserves the monomorphisms of that category. So all we have to do effectively is take the conventional definition of a double push-out rewriting system and just enforce the constraint that all the monomorphisms have to be preserved by the embedding functor, and we can translate all of the kind of usual apparatus of algebraic graph transformations to this category of typed hypergraphs, which is effectively what we're doing. So that gives us a way to define in a purely compositional way what it is that we're doing when we apply these hypergraph transformations. But actually, everything I've said so far is a grand simplification of the reality of what's going on. So, of course, when I showed you before something like this, I kind of pretended that there was a unique sequence, that there's sort of a deterministic progression from one hypergraph to the next. But of course, in reality, that's not going to be true, because a rule like this one will in general be able to match in many, many different places on any given hypergraph. And the order in which that rule gets applied is going to matter in general, right? So different updating orders, different sets of kind of non-overlapping subhypergraphs to which you apply the rule will yield different non-isomorphic hypergraphs in the corresponding evolution. So in reality, what you have is not so much just a path of evolution history, but really a kind of a directed graph. We're going to assume for the moment that it's a directed acyclic graph, although in reality it might not be. So what we can call that thing a multi-way evolution graph. So it's a directed acyclic graph in which every vertex is just a hypergraph, some object of our abstract rewriting system. And every directed edge is an application of the rewrite relation. So in other words, two hypergraphs A and B are connected by a directed edge if and only if there exists a direct typed hypergraph transformation from A to B, and they're connected by a directed path if there exists any hypergraph transformation from A to B. In other words, they're related by the reflexive transitive closure of the rewrite relation, or there exists a sequence of direct hypergraph transformations that gets you from A to B. So one of these, if we construct one explicitly, this is what one of these multi-way evolution graphs looks like. It's actually the multi-way evolution graph for the same rule that I showed you on one of the previous slides. So we get this directed acyclic graph. Here you can see vertices are being merged on the basis of hypergraph isomorphism. And this multi-way evolution graph effectively therefore parameterizes the space of all possible updating orders or rewriting sequences that could have been applied to a given hypergraph. And then, so for instance, the particular rewriting sequence that I showed you on one of the earlier slides then just corresponds to a particular path through this multi-way evolution graph. In fact, it corresponds to precisely to this path that's been highlighted. And so these multi-way evolution graphs have some interesting compositional properties. So at a basic level, one way that you can think about them is that they are effectively, that each one of these multi-way systems or multi-way evolution graphs is an F coalgebra for the power set functor on the category set. So the reason for that is if we consider this rewrite relation in generality to be given by an indexed union of subrelations, then what we have is a bijective function from the set of possible hypergraphs to a subset of the power set of possible hypergraphs indexed by the set of labels. So we have a function that looks like this. And this means that if we consider the power set construction to be a covariant endofunctor on set, then one of these abstract rewriting systems is an object, which is effectively the set of possible hypergraphs equipped with this morphism of set, and therefore provides us with an F coalgebra for the power set functor. But actually, there's a lot more going on than just that. So in particular, one of these multi-way evolution graphs has the structure of a compact closed dagger symmetric monoidal category. So I won't have time to kind of take you through in detail how we derive all of those properties. Again, you can read our first CX paper if you want to get more details about that. But I can give you a sort of flavor of roughly how that works. And the basic idea is that in one of these multi-way evolution graphs, there are two ways that you can compose rewrite sequences, right? You can compose them sequentially or you can compose them in parallel. And that fact gives you a natural monoidal structure on the associated category. So to be a bit more formal about that, if we consider the category of multi-way evolution graphs, which we'll call mu graph, then if we have two typed hypergraph productions, P1 and P2, and they're E-related, in other words, they're effectively concurrent, so we have a transformation from hypergraph G to hypergraph H to hypergraph G prime, and where those transformations are given by productions P1 and P2 respectively, then they can be composed to obtain an E-concurrent production, which I'll call P1 star P2, which gives us a direct transformation between G and G prime. And that gives us if we consider now P1 and P2 to be morphisms in the category mu graph, then P1 star P2 gives us kind of the ordinary sequential composition of those morphisms. On the other hand, if we have productions P1 and P2 that are sequentially independent, so if there exists two sequentially independent transformation sequences from G to H1 to G prime and G to H2 to G prime, so that one has something that looks like that, P1 to P2 or P2 to P1, then these two transformation sequences can be composed using the parallelism theorem of algebraic graph transformation theory to obtain a parallel production, P1 plus P2, which again gives us a direct transformation from G to G prime. And this parallel production, P1 plus P2, we can think of as being like the monoidal product of P1 and P2. So we have both sequential composition and parallel composition of morphisms, or monoidal composition of morphisms. And it's not particularly difficult to show that these operations satisfy the requisite sort of associator, uniter, symmetry, isomorphism properties that you need to get a symmetric monoidal category. And again, with a little bit more effort, you can show that taking hypergraph duals gives you a way to induce a compact structure, and the fact that you can take one of these rules and you can swap the left-hand and right-hand sides around, so you can so for any given rule you can construct its inverse, gives you a natural involutive functor on this category that equips it also with a dagger structure. So again, I won't go through the details of that, but one can indeed show that what we obtain is a compact closed dagger symmetric monoidal category where the dagger structure, the compact structure, and the monoidal structure all satisfy kind of the requisite coherence conditions. And okay, I should mention, just as a sort of teaser for for some stuff I'm going to say a bit later, that fact that one of these multi-way evolution graphs effectively has this compact dagasymmetric monoidal structure is going to become relevant later when I talk about kind of possible relationships with the foundations of quantum mechanics and things like that. Okay, in addition to the rewriting formalism that we're dealing with, there's a whole kind of separate, more or less dual picture of what's going on, which we can think of in terms of causality. So in some cases, for instance, okay, if we look at something like this, there'll be certain cases where a particular rewriting rule, a particular edge here, could only have been applied if another edge had previously been applied, or another rewriting rule had previously been applied. And there'll be other cases where two rewriting rules are completely independent of each other, where it doesn't matter which one got applied first, and there's no kind of there's no sequentiality to that rewriting sequence. So we can encode the difference between those two situations in terms of a sort of causal structure. So a natural way to do that is to introduce a directed acyclic graph, which we'll call a causal network or a causal graph, in which every vertex is now an application of an update rule. In other words, every vertex is a hypergraph transformation, and in which every directed edge is a causal relationship between those transformations. And so in the most naive case, the way that we can infer that the two updating events are causally related is if the input for one has a non-trivial intersection with the output of another. So in other words, if the input for event B makes use of hyperedges that were produced by the output of event A, then more or less by definition, event B couldn't have been applied unless event A had previously been applied. And so we can say that that sort of A and B have a causal relationship, that A arrows B in this causal network. And so if we take this causal network and we transitively reduce it, we get the Hasse diagram for some strict partial order relation that turns out to have very similar properties to the causal partial order relation that one cares about in doing sort of analysis of the conformal structure of space-time. And I might talk about that a bit later when I get to these more speculative relationships to fundamental physics. Okay, so this is what, in practice, one of these causal graphs actually looks like. This is, again, the same rule that we were, or actually not the same rule, it's a similar rule to the one we were looking at before. So you can see here on the left, each one of these yellow boxes is a particular rewriting event, is a particular update on one of these hypergraphs. And each one of the orange edges between them is a place where hyperedges have been shared between the input of one and the output of another of these events. And so if we grow this directed acyclic graph a bit more by running the system a little longer for 5 steps, we get something that looks like the thing on the right there. And again, as I say, if we take the transitive reduction of this gives us precisely the Hasse diagram for the causal partial order relation on one of these hypergraph rewriting systems. So we can combine these two ideas together, right? So because between every pair of hypergraphs, between every pair of states, effectively, there is an event, there is a rewriting rule that's being applied, and for any rewriting rule, it can be causally related to any number of other rewriting rules. We actually get one of these things here, which we call a multi-way evolution causal graph, which incorporates both the abstract rewriting structure, which is the stuff that you see in blue and gray. So every one of the blue vertices is a particular hypergraph state, and every one of the gray edges is a rewriting event between two hypergraph states. But also it incorporates the causal structure. So every one of these yellow boxes is a rewriting event, and every one of these orange edges is a causal relationship between these rewriting events. So in effect, everything we might conceivably care about related to this rewriting system is encoded in the structure of one of these multi-way evolution causal graphs. Okay, but again, what is a multi-way? If we already know that one of our multi-way evolution graphs, which is produced, as I say, from this F coalgebra for the power set functor, is one of these compact dagasymmetric monoidal categories, what is a multi-way evolution causal graph? Well, it turns out that this has a very natural encoding in terms of a symmetric monoidal 2 category. So to see how that works, okay, let's first look at what it means for two productions to be causally related in a compositional sense. So again, if we just take two spans of monomorphisms, K1 to L1, K1 to R1, and K2 to L2, K2 to R2, then we can say that they're causally related if L2 minus K2 has a non-trivial intersection with R1 minus K1. So again, that's just the analog of saying the input for production P2 has makes use of hyperedges that appeared in the output of production P1. And so we get this category mu, which I'm going to call mu cow graph for multi-way evolution causal graphs. And this gives us a weak 2 category. So in effect, what's happening is that every transformation between hypergraphs gives us a 1 morphism. and every causal relationship between those rewriting events gives us a 2-cell between those 1 morphisms. So to be a bit more explicit, what we've got are 2 different monoidal structures. We've got the ordinary monoidal structure that occurs from the fact that we can compose these rules, these productions in parallel. That gives us the 1 cells. We've also got the separate monoidal structure, which arises from the fact that we can take 2 causal relationships between those productions and compose those in parallel. In other words, we can compose 2 cells and we can compose 1 cells using different monoidal structures. And it turns out we were able to show in the second and third of our of the papers in the sequence that this second monoidal structure gives us specifically what's called a partial monoidal structure. This makes use of the work of Bob Coker and Raymond Lau. And so a partial monoidal structure for us just means it's a partial bifunctor. In other words, if we consider the category cow graph of just which is the category not of multi-way evolution causal graphs, but just of causal graphs, then the monoidal structure on core graph is a partial bifunctor in the sense that if we take a subcategory of core graph and take its Cartesian product with itself, then and we consider a bifunctor from that product category onto the full category core graph, then that is in effect what our partial monoidal bifunctor is. And so this subcategory of the full kind of Cartesian product category is what we call the domain of definition of that partial monoidal structure. And so in particular, there are various sort of technical conditions that are required to be satisfied in order for this to be a true symmetric strict partial monoidal category. The unit object has to be terminal. There has to be a unique morphism for each object A onto the unit object. And the monoidal product has to exist only under certain conditions with respect to compositions with this unique morphism. But we were able to show that in fact these properties are indeed satisfied for the case of one of our causal graphs. And so what we get is indeed a symmetric strict partial monoidal category, effectively the monoidal category analog of saying that that one of these causal graphs encodes a partial order relation. Okay, so what I've been able to what I'm trying to convince you of here is that it is in fact useful to think of, just as it's useful to think of multi-way evolution graphs as being, monoidal 1 categories, it's actually useful to think of these multi-way evolution causal graphs as being monoidal 2 categories. So an obvious question is, can we go further? Does it make any sense to go further? We know what the 2-category structure is like and what it means, but what do the kind of higher category, what are the higher categorical analogs of one of these hypergraph rewriting systems?
Can I ask a question?
Please, yes.
So in your causality, can you ever get a cycle in that one rewrite rule rewrites to something which makes another one apply to then go back? And can you get cycles at all? And does that work within the category, or do you just ignore those cases?
That's a really, really good question. Okay, so it turns out that, for reasons that may or may not be obvious, you can get cycles in one of these in these causality relations, but they will happen only when you get cycles in the associated multi-way system. So if it can be the case that a given hypergraph state can be rewritten to one that was previously derived, then you will get then you'll obviously get a cycle in the causality relations, but that can't happen otherwise. So the answer is we are effectively only considering those multi-way evolution graphs for which those cycles don't exist. And the reason is more or less, as you say, that kind of all the categorical properties of our causality relations and indeed the categorical properties of our multi-way systems basically fall apart as soon as these graphs become cyclic. The reason being, we no longer have a valid partial order relation, as soon as there are cycles, because it no longer obeys anti-symmetry or asymmetry. And also all of the algebraic properties of how we go about composing these productions and composing these causal relations, those all assume that, effectively we have an acyclic relation. So the short answer to your question is yes, it can happen, but we are effectively assuming only rules where it's guaranteed that won't happen. And there are other kind of hacky fixes for that. So for instance, when I showed earlier one of these multi-way evolution graphs, I mentioned that we were merging these vertices based on essentially hypergraph isomorphism. One hacky fix that you can do is you can just say only merge vertices based on hypergraph isomorphism if they exist at the same time step. And then that rather trivially eliminates the case where you can get cyclicity in the multi-way system, and that in turn eliminates the case where you can get cyclicity in the causal relations. But anyway, in either case, we definitely view cyclicity of causality as being a pathology rather than and something that we want to avoid, rather than as something that is sort of permitted.
Some way to figure out when that occurs, right? Because the rewrites are not completely independent because they are kind of overlapping, right?
Right. So it's there isn't. Sorry, please go on.
No, keep going. Sorry.
So I think you started talking and I was still going. I think I missed the first part of what you said. But I agree that it is difficult. In fact, I'm pretty sure there isn't a sort of finite decision procedure that could determine whether a given hypergraph rewriting system is going to be cyclic or not. Because as far as I know, I believe it would be the case that even for a fixed rule size, you could have arbitrarily large cycles. So, even the fact that you've run your system for 1 million steps and it hasn't produced a cycle is no guarantee that it won't somehow go back to some previous state if you keep on running it. I guess the only cases in which that isn't going to be the case are ones in which in which the hypergraph always grows or something like that. But I suspect in general that there can't be a sort of a simple decision procedure for determining that. So in a sense, it's something we just have to try to avoid, as I say, either by explicitly screening for rules which we can prove can't go into cycles, or as I say, by modifying essentially our merging criterion so that we only merge on a given time step, and that again guarantees acyclicity of the multi-way system.
Okay, thank you.
Yeah, no problem. That's a really good question. Sorry, was there a chat question? Yes, sorry, Jules, you're saying probably for halting problem related reasons. Yes, I completely agree. I think it's yeah, I know. I think that's exactly right. I think you can build. There probably is a fairly straightforward diagonalization argument that would tell you that for any claimed algorithm that could determine whether a given hypergraph rewriting system goes into a cycle, you could always construct one that violates that. You could always diagonalize to construct one that disagrees with those predictions. I think that's probably true. There probably is also a way to prove it using sort of Rice's theorem argument or something. Anyway, yeah, if I had to guess, I would put a lot of money on it being an undecidable problem. Okay, right. So yeah, what I was saying was, so okay, we've seen that thinking about one of these multi-way evolution causal graphs as a monoidal 2 category is useful. It gives us a way to see kind of the compatibility between the rewriting structure and the causal structure. But what about, is there any sense, or is there any use in going to kind of higher categories? Well, it turns out there might be. And at the very least, it gives us there are some interesting algebraic properties that kind of emerge when we consider sort of higher categorical versions of what we're doing. So let's think of a very simple rewriting system. Let's forget about hypergraphs for a moment, because they introduce a bit of unnecessary complexity. Let's just consider really simple string rewriting systems. So let's consider a string substitution system. A goes to AB, and here we have sort of the multi-way evolution graph for that string rewriting system. And so each one of the directed paths in the system we can think of as being a proof of some proposition, a proof that such and such a string can be derived from some other string given the rule A goes to AB. So in this case here, we've got a red path representing a proof of the proposition that AA goes to ABBB, ABBB. And here we've got a yellow path that corresponds to a different proof of the same proposition. So now if we think of each of these paths as being a kind of, because we have a multi-way evolution graph, each one of these paths is really a one morphism in the associated category. We could now think of a sort of a transformation that maps points on one of these paths to points on the other path. So in other words, we can construct a proof that these two proofs are equivalent by building a bijective correspondence between the points on one path and the points on the other path. So we get essentially a kind of homotopy construction, which I'm showing in purple here, that maps every vertex in one path to a corresponding vertex on the other. And so there are several ways that we can introduce those homotopies. We could either directly introduce the directed edges into the multi-way evolution graph, which is kind of a cheating ad hoc way to do it, or we can introduce new effectively higher order rewriting rules that say this state maps to this state maps to this state, etc. And then we get a new sort of higher dimensional version of the multi-way evolution graph that we started with this homotopy map built into it. And that's the thing that you see on the right here. So you can also see that in the thing on the right, there are these new transformations that weren't possible in the old system because these higher order rewriting rules hadn't been introduced. And so this gives us a way to introduce effectively two cells between these one cells that correspond to proofs of equivalence between proofs. And this is not just, I mean, we can go further, right? So once we've done something like that, we can consider a case like this, where we have 4 proofs of 2 different propositions, 2 equivalent proofs of one proposition here shown in red, and 2 equivalent proofs of a different proposition here shown in yellow. And then we can construct a 3-cell between the corresponding 2 cells. So here's one way to see that. So we've got purple edges. Those are our 2 cells that we saw before, but those are 2 cells between the red paths. We've got orange paths that correspond to 2 cells between the yellow paths, and then we've got these lighter arrows that are corresponding to 3 cells between those 2 cells. So here we're gluing 2-dimensional faces together to form some kind of cube. Here's a slightly different way to visualize exactly what's going on. The purple arrows here correspond to our 3 cells, and the 2 cells are the red and yellow paths. And so again, we can make a very similar picture to the picture we made before. So here we're introducing these higher homotopy maps. So on the left, we've got homotopy maps included in this cheating ad hoc way, and on the right, we've got the 3-cell homotopy maps introduced in this kind of in this more natural way by introducing these higher order rewriting rules. So what I'm trying to tell you is that in effect, what we're doing is, anytime there exist multiple paths that lead from one vertex to another vertex in this multi-way evolution graph, we can think of those as being equivalent proofs of the same proposition in some kind of type theory. And then we can essentially use homotopy type theoretic techniques to map one of these proofs onto the other, to map one path onto the other. And that naturally, in the multi-way system context, that naturally corresponds to introducing these higher order rewriting rules that let us map from points on one of these paths to points on the other path. And so long as the rewriting system has an appropriate structure, so long as these higher order rewriting rules are admissible, and we don't and this process doesn't terminate, in other words, where we don't end up just with a sort of trivially confluent rewriting system. So as long as the underlying rules are sufficiently complicated that we can keep on going, adding these higher order rewriting rules and never end up with a confluent term rewriting system, then effectively there's nothing to stop us from going to some kind of infinite limit of this process. So we can see this a bit more formally. When we take 2 paths in this multi-way evolution graph and we map points on one to points on the other, what we're doing is effectively constructing a double category. We're constructing a category where the objects are objects of the original category we started from. The vertical morphisms are the morphisms of that category. The horizontal morphisms are the objects of this higher category, and the 2 cells of the double category are morphisms of this higher category D1. So in effect, what we're doing is we're introducing commutative squares of this form. And if we also introduce rules that cause all of our rewrite relations to be invertible, so effectively we take our typed hypergraph production and we swap the object L and R, so we get an inverse rule that gives us, as I mentioned before, gives us this involutive functor, it gives us this dagger structure on our multi-way system category. Then if we also include those, we naturally obtain a double groupoid. And we can keep going. We can obtain a 3-fold category if we sort of recursively apply this procedure again. In which case, now what we're doing is, rather than kind of taking one of these squares and gluing two of these one morphisms together, what we're doing is we're taking 2 of these 2 cells and we're constructing a 3-cell that glues those 2 squares together in the form of one of these commutative cubes. And as I say, we can just keep going. So in other words, so long as these higher order rewriting rules are admissible up to some order n-1, we can construct an n-fold category just by kind of recursively repeating this procedure. And as I mentioned, for rewriting systems that don't become confluent after a finite number of introductions of these higher order rewriting rules, we can take an n goes to infinity limit. And if we also, and that gives us sort of a weak infinity category. And if we include invertibility relations that let us go from L to R and R to L, and so long as those rules are admissible, then we obtain an infinity groupoid. And that infinity groupoid that we construct from one of these base rewriting systems, one way that we can think of it from a sort of intuitive point of view is that it's encoding essentially all possible admissible transformation rules of a particular signature. And so we kind of informally refer to these things as ruleal multi-way systems. They're multi-way systems in which all possible rules of a particular class are instantiated. And then we can look at sort of compositions of, we can look at collections of those Rulli or multi-way systems in which effectively all possible rules, not just of a given signature, but all possible rules of, of all possible signatures are instantiated. And that gives us effectively a classifying space of these infinity groupoids, which has the formal structure of an infinity one topos. And that's, again, immediately interesting because that's kind of the setting of classical homotopy theory. And okay, you might say, well, why would we care about any of this higher categorical structure? This seems very, very far removed from anything you might want to use a hypergraph rewriting system for. Well, actually, there are some interesting practical applications of the use of this sort of higher homotopy, higher category construction, which I'll get to towards the end. But the real reason that we were interested in it in the context of our program was that we were interested in understanding the relationship between these hypergraph rewriting systems and the foundations of physics. In other words, what we wanted was to get to the point where we could, for instance, claim that one of these hypergraphs has the structure, we could think of one of these hypergraphs as being like a kind of discrete version of a Riemannian manifold, or we could think of one of these causal graphs as being like the discrete version of a Lorentzian manifold, or even that we could think of one of these multi-way evolution graphs as being like a discrete version of a projective Hilbert space. And the question is, how could we go about proving something like that? How could we prove that, say, a hypergraph inherits enough of the spatial structure of a Riemannian manifold that we can treat it like a Riemannian manifold in some appropriate limit? And it turns out that this relationship to infinity groupoids gives one a formal way to do that because of the so-called Grothendieck hypothesis. So because these weak infinity groupoids have the structure of kind of higher homotopy spaces, because in a sense one can think of them as being like a model of a topological space. Every time we take one of these multi-way evolution graphs, we are in effect taking a fiber or a global section through one of these infinity groupoids. And under some fairly weak assumptions, we can show that that global section inherits enough of the spatial structure from the structure of the infinity groupoid that the resulting objects like multi-way evolution graphs or causal graphs or hypergraphs inherits a certain degree of spatiality. And that in turn gives us formal justification, for instance, for thinking of hypergraphs as being like kind of skeletonized versions of Riemannian manifolds and things like that. Again, if you want to see more details of exactly how that works, you can read the latest paper that Xerxes and I put on the archive just a couple of weeks ago. So to tell you a little bit about what I mean and why we care about this in the context of physics, it turns out one can show that because one of our multi-way evolution graphs has this structure of a compact dagger symmetric monoidal category, which is the same as the structure of the category FT Hilb, it inherits enough of the kind of compositional structure of the category of finite dimensional Hilbert spaces that, for instance, one of these multi-way evolution graphs can be interpreted in some appropriate, under some appropriate conditions as being like the evolution of a Hartle-Hawking wave function. So in effect, one can think of each one of these hypergraph states as being like a sort of a specification of a classical state of some space-like hypersurface. The kind of collection of hypergraphs on a particular layer of this multi-way evolution graph is then a kind of superposition of those classical states. So each one of these layers is telling us a quantum state of a sort of a given space-like hypersurface, or in effect, it's telling us the quantum state of a gravitational field on a space-like hypersurface. And then the evolution from one to the next is then given by some discretized version of the Hartle-Hawking wave function from quantum mechanics. And the thing that justifies this whole construction is the inheritance of that spatial structure from the category FT Hilb. And a very similar thing happens for the case of hypergraphs as well. So we can show that hypergraphs inherit the compositional structure of Riemannian manifolds. So if we can consider a category of Riemannian manifolds whose morphisms are smooth maps such that the symmetric bilinear form on the tangent fiber at each point is positive the symmetric bilinear form of this structure at each point is positive semi-definite, then the spatiality from that category is sort of inherited down from this infinity groupoid to all the lower order objects. And that gives us a formal way of justifiably treating these hypergraphs as being like discrete analogs of space-like hypersurfaces in physics. So for instance, we can use that to find examples of hypergraph rewriting rules that obey the Einstein field equations in the continuum limit. So as a kind of nice example of that, here's an example of a pair of Schwarzschild black holes that are being collided together, where the dynamics is given entirely by hypergraph rewriting rules. So these are just ordinary directed hypergraphs. They're being colored here based on a discretized version of the Schwarzschild conformal curvature. And if we continue to run this hypergraph transformation system, if you look at the highest resolution version on the right here, you can see these two simulated sort of Schwarzschild black holes merge, and we get this kind of gravitational ring down, and we can do effectively discrete versions of general relativity simulations purely using hypergraph transformation rules. And again, as I say, the thing that formally justifies us being able to do that is the fact that these hypergraphs are inheriting spatiality from this infinity groupoid structure that we get by iterating this kind of higher categorical construction. Okay, so that gives us I'm not going to talk too much about physics. I realize this is an MSP talk. I just wanted to explain why we, in the context of sort of thinking about the foundations of physics and trying to reduce the foundations of physics to something compositional, why we care about hypergraph rewriting and why we care about introducing these higher order morphisms in the context of hypergraph rewriting. And the reason is because it gives us this guarantee of spatiality that we need to justify a lot of these constructions. But okay, so just to finish, I'd like to talk a bit about an actual kind of practical computer science application of these higher categorical ideas. Why is it useful to think about hypergraph rewriting as being anything but a one category? Well, it turns out, for instance, by thinking of these hypergraph rewriting systems as monoidal two categories, it lets us do automated theorem proving. It lets us do automated diagrammatic reasoning in a way that's significantly more efficient than would be possible otherwise. So to show you what I mean by that, imagine you have a multi-way evolution graph that looks like this, and it has causal relations that are shown in orange here. And you want to do kind of diagrammatic theorem proving over this multi-way system. So you want to be able to prove, the proposition that such and such a hypergraph can be mapped to such and such another hypergraph. Well, in ordinary kind of automated theorem proving, you would treat kind of all transformations as being equal. So if you wanted to introduce lemmas into your, if you wanted to introduce substitution lemmas into your abstract rewriting system, they would all be kind of treated on equivalent footing. But when you have this monoidal two-category structure, you can be a little bit more discerning than that. You can say, let me only introduce substitution lemmas that kind of maximize causal relations. So in other words, if we have a choice between two different paths to take through this multi-way system, we can choose to take the path that has the highest density of outgoing causal edges. Why would we want to do that? Well, because when we want to when we're trying to introduce lemmas to our diagrammatic rewriting system, we want to introduce lemmas that have the greatest effect on the shortening of subsequent proofs. And more or less by definition, the lemmas that will have the greatest effect on the shortening of subsequent proofs are the ones that are most densely causally connected to events that occur in the future. And so it gives us a very nice heuristic for doing lemma selection in the context of doing automated diagrammatic reasoning. So to see a bit more formally how we do that, what we did was we in our second and third ZX calculus papers, we took this construction of a refutation complete proof calculus for first order logic with equality due to Bachmeier and Ganzinger. We extended it to diagrammatic logics, and we introduced these rules of selective resolution, selective superposition, and ordered resolution, which are effectively taking the ordinary kind of resolution and superposition calculus rules from equational logic and introducing this kind of selection function, which we called S, which is essentially saying that if we have a choice between two occurrences of an equation that we want to add to our rewriting system, we select the one that's maximal with respect to the causal selection function. So in other words, we always select the path in the multi-way system that maximizes the causal effect, that maximizes how effective this particular event is going to be in shortening the proofs of subsequent propositions. So it gives us a slightly more refined way to do diagrammatic reasoning. So here's an example of a proof graph that was constructed using the automated reasoning system that we built. It's proving a simple proposition that says that this initial hypergraph maps to this final hypergraph subject to this rewriting rule. And we can apply this to solve very practical problems, for instance, in quantum information theory. We can use the fact that these we can exploit the fact that these multi-way evolution graphs have this structure of FD Hilb. They have this compact Dagger-symmetric monoidal category structure to apply them to solve problems in categorical quantum mechanics and quantum information theory. So the first thing we want to do there is to say, well, our hypergraphs that we've considered so far are closed hypergraphs, but actually both open hypergraphs and closed hypergraphs. Okay, sorry. When I say closed, I mean that there are no kind of dangling hyperedges. There are no hyperedges coming out without vertices bounding them. But both open hypergraphs and closed hypergraphs are special cases in this category of typed hypergraphs that we built right at the beginning. So for any given hypergraph, there's a hypergraph that is equipped with a total hypergraph morphism from the given hypergraph G to the type hypergraph TG. And we have a type graph that looks like this that we can use to distinguish between what we call true vertices, those are vertices that actually exist, and what we call dummy vertices, which are effectively the kind of invisible vertices that bound the edges of that bound the kind of the ends of dangling hyperedges. So open hypergraph string diagrams are a subcategory of this slice category, where hgraph designates the category of closed hypergraph string diagrams. So all of the techniques that we've developed for the case of closed hypergraph string diagrams can also be applied to open hypergraph string diagrams, again with kind of with a minimal amount of modification. And the significance of that is that the so-called ZX calculus, this diagrammatic rewriting system for string diagrams that represent linear transformations between qubits in finite dimensional Hilbert spaces, that gets used a lot in sort of categorical quantum information theory, those ZX diagrams are instances of essentially open typed hypergraphs. So we can think of them as being a special case of open typed hypergraphs. So all of the rewriting methodology that we've developed so far can also be applied to rewrite ZX diagrams in an automated way. So the only slight complication is that ZX calculus is actually a higher order diagrammatic logic. It's not a first order diagrammatic logic because it has rule schemas like the fusion rules or the bialgebra rules that are really infinite kind of collections of first order rules. So the first thing we did was we used this construction that's due to Manfred Kerber to define a morphism that lets us map from an nth order diagrammatic logic to a first order multi-sorted logic in such a way that the set of formulas gets preserved. So we can reduce any set of formulas in the higher order diagrammatic logic to an equivalent or an equisatisfiable set of formulas in the first order multi-sorted logic. And that lets us take the causal sort of optimizations that I defined in the previous slides and apply them to the case of automated rewriting of ZX diagrams. And so here's an example of a simple theorem in the ZX calculus. It's a statement that the C0 gate, which is the thing on the left here, is unitary. So each one of these vertices is either a Z spider or an X spider. In other words, a sort of generalization of a rotation around the Z axis or the X axis of the block sphere. And then here on the right is the corresponding proof graph that is the kind of automated diagrammatic proof that this proposition is true. And so here, this is us applying the automated diagrammatic rewriting system that we developed for the case of closed hypergraphs, but now being applied to the case of these open string diagrams for the ZX calculus. And the significance of that is that when we incorporate this two-category structure, so we take into account the causal relations between these events, and we use that to optimize which lemmas we're adding to our automated rewriting system, we see a dramatic improvement in both time complexity and proof complexity. So here's a somewhat modest improvement that you can see. What we did is we randomly generated quantum circuits containing only Clifford gates with sizes ranging from 0 to 3,000 gates. And we looked at how long it would take for an automated reasoning system to reduce that circuit down to a pseudo-normal form. And you can see that without optimization, so if we only think about the one category structure, then you can see that at the top end it takes about 4 seconds, and you can see that we roughly halve that if we include the two category structure. If we include knowledge of these causal relations and we use that in order to optimize which lemmas we're adding, we get about a factor of 2, an improvement in the time complexity and a similar improvement in the proof complexity. And in fact, we looked at other cases that are somewhat more demanding, like the reduction of T count in non-Clifford quantum circuits, and we get even more dramatic savings. And in general, what we were able to find is at the top end, we were able to achieve a roughly quadratic speed up, both in time complexity and in proof complexity, by including this a knowledge of this two category structure in our automated rewriting algorithm. So what I'm trying to convince you of there is that it's, thinking about these kind of higher categorical aspects of hypergraph rewriting systems isn't just of interest from a kind of purely theoretical standpoint of telling us about, where spatial structure comes from in these discrete models of quantum gravity, which of course is interesting in its own right, and it's why we first started pursuing this direction. But it also seems to be useful to think about higher categorical aspects of hypergraph rewriting for doing very, very kind of down-to-earth automated reasoning and for kind of optimizing things like circuit simplification algorithms in the context of quantum information theory. So there are lots of other implications, both theoretical and kind of practical, that I could talk about. But seeing as though we're almost at the top of the hour, and I think there's a chat question, let me stop the kind of structured part of the talk so we can go into more